Hello there. In this lesson, we're going to look at different ways of expressing concentration values for solutions. So you know that sort of qualitatively, the difference between dilute and concentrated is that dilute would have less solute per unit of solution and concentrated would have more. But you can be a little more specific than that, and we're going to look at a bunch of ways in which people have done that. So solution concentrations can be represented in a variety of ways. The most common that we'll use in chemistry class is going to be moles of solute per liter of solution. And so that's called molarity, and it's given the symbol M. So if there were like 5 moles per liter, that would be 5 with a big M. They mean the same thing. So let's see if we can work out the concentration of a solution made by measuring this much, 7.19 grams, of this compound, copper 2 sulfate pentahydrate. And there's the molar mass there, 249.7-ish. So we'll say, and we want to know what the molarity will be. And it's been dissolved in this flask, this volumetric flask, 250 milliliters. So the volume equals 250 milliliters, which is 0.25 liters. So that's the liters part. And the moles is 7.19 grams, and the molar mass was 249.7 grams per mole. And so that works out to be 7.19 divided by 249.7 equals 0.0288 moles. And then, so the molarity would be that 0.0288 moles in 0.25 liters. And that equals 0. What's my measurement here? It's 3 digits. So 115 moles per liter. Moles per liter. Or 0.115 big M. Great. Now when you dissolve ionic compounds into a solution, you can end up with more ions than you had of the units of the compound that you started with. So if it's something like sodium chloride and you dissolve that, for every 1 sodium chloride, you're going to get 1 sodium and you're going to get 1 chlorine. And so the concentration of sodium chloride will also be the concentration of the sodium and the concentration of the chlorine, right? So if this is 0.5 moles per liter that you dissolved, well, you're going to have 0.5 moles per liter of sodium, and you're going to have 0.5 moles per liter of the chlorine. However, when you have a compound that has more than one of a particular ion, then that changes. So you can make a solution that is 0.5 moles per liter magnesium chloride, but when you dissolve that, you're going to get more chlorines than you do magnesiums, just because of the way they stick together, right? And so you will still have 0.50 moles per liter of magnesium, because for every one of these that dissolve, you get one of these. But because you get 2 chlorines for every one of these magnesium chlorides that dissolve, the concentration of chlorine will be 1 mole per liter, right? Because you're going to have to multiply it by 2. So times 2. So keep an eye out for that when you're looking at the concentration of ions. Make sure you look at the formula and see what happens to them when they dissociate. So molar concentrations are conversion factors just like anything else. The only thing that students sometimes get a little tripped up on is the big M thing. So remember, over and over again, big M means moles per liter, right? And so that's a conversion, right? You can convert liters to moles or moles to liters using that value. So it says what volume of the acid shown in the picture contains 1 gram of HCl. So we'll say volume and 1.0 grams of HCl. And so we know that HCl, the Cl off my periodic table here, has 35.4. So plus another 1 for the hydrogen, so 35.4, 1 gram per mole. So the molar mass here is 36.4 grams per mole of HCl. And then the molarity of this is 1 mole per liter, right? So 1 mole is 1 liter, and so we can work out the volume in liters by doing this little factor label calculation. Grams cancel out, moles cancel out. I'll end up with liters. That's supposed to be an L. So 1 divided by 36.4 equals, everything else is a 1. So that's 0.0275 liters, which, if you change that to milliliters, is 27.5 milliliters. There you go. Another method of showing concentration is used in a variety of places. If you hear about the changing amounts of carbon dioxide in our atmosphere. Carbon dioxide is a trace gas. There's very little of it, but it has a pretty significant effect on the climate. And so often it's given in terms of parts per million or parts per billion as the concentration changes, just to show that change. Another place you can see this is on the side of any like water bottle that you might buy. And have a look on the side there, have a look for the analysis part, and it'll give you the concentration of various ions that are in this solution in terms of parts per million. ppm means parts per million. And it's pretty simple calculation. You just take the mass of the whole thing, the whole solution, and the mass of the solute, what's being dissolved in there, divide those and multiply by 1,000,000 for parts per million, multiply by 1,000,000,000 for parts per billion. So let's try that with mercury and seawater, which is an issue as mercury has been thrown into seawater from toxic sources for quite some time, and it can cause problems as it biomagnifies up the food chain. So let's have a look here. If we want the ppm concentration of that, we would take the 0.0332 grams of mercury divided by the 1,500 grams of solution, which is the seawater, and multiply that by 10 to the 6th. And that would give us, let's see here, 0.0332 divided by 1,500 equals that times 10 to the 6th. So I get 22 parts per million. I guess we got, yeah, two sig figs there. 22 parts per million. And so obviously that's probably the best way to express concentration with this value. If we change it to parts per billion, it'll be the same calculation. Just at the end, you're going to multiply by 1,000,000,000, which means you're going to add 3 zeros to this, which means you're going to end up with 22,000 parts per billion. So probably the best choice would be use parts per million for this size of measurement. Yeah, same exact thing on the top and bottom. So a percentage is another way of representing the concentration of a solution. It can be a percentage by mass, where both measurements are in grams. It could be a measurement by volume, where both measurements are in liters or milliliters. Or it could be a mixture, like this one with the saline solution, where it's mass on the top and volume on the bottom. And so you could use this relationship for any of those. Just keep an eye on this little m over v, or m over m, or v over v to tell you what units to use. So if it's m over v, that means mass on the top and volume on the bottom. And then you can work out any relationship by rearranging that equation. So it says the saline concentration is 0.9% mass over volume. What is the mass of sodium chloride dissolved in the bottle? So the mass of the solution. This is a 500 milliliter bottle. So we don't know the mass of the solution, but we do know it's a 500 milliliter bottle times 100, and we know it's 0.9%. So all we need to do is rearrange this. So x equals the 500 times the 0.9% divided by the 100, and you would end up with, let's see here, 500 times 0.9 divided by 100 equals 4.5 grams of NaCl in this whole bottle. Okay. Now, if you recall, an alloy is a solid solution, a homogeneous mixture of metals. And most of the metals that you would see in your everyday life aren't 100% pure, but rather an alloy, a mixture of metals that gives them properties like strength, like with steel or the gold in jewelry, that sort of thing. So these percentages are mass percentages, right? Mass on the top, mass on the bottom, and you can use those to solve for various quantities that are measured this way. So it says what mass of gold would be an 11 gram 18 karat necklace. So 18 carats is 75% gold, and we want to know how much gold is in there. So the solute there is the gold, although it is in the higher quantity. Anyways, so the bottom part here is the mixture, this necklace, and the percentage is 75%. Great. So we got 75% equals X amount of gold over 11 grams of necklace times 100. And if you want to find X, same thing that we did last time, 75% times the 11 grams divided by the 100 that was on the other side there. And we get 8.25 grams of gold. It's supposed to be U. Our last percentage is the percent of volume. So it's done the same way as all those other percentages, the solute on the top and the solution on the bottom, only this time it's volumes rather than mass or a mixture. Okay, this is often used when you're talking about alcoholic beverages. They will have a percentage that is a volume percentage that shows how much ethanol is in the spirits or beer or wine or whatever it is that it is found. So you can use the relationship the same way as we did before. This time we're looking for the volume of the wine. So the wine is the solution. And so we're looking at this guy, and it looks like 12% ethanol in the wine. So we've got 12% and equals the volume, the 5.0 milliliters of ethanol, in X milliliters of wine times 100. And so to rearrange that, X equals 5 milliliters divided by the 12%, that's a 12 times 100 equals, okay, let's see what that comes out to. 5 divided by 12 times 100 equals, and that means you would need to drink 41.6 milliliters of wine in order to consume the 5 milliliters of alcohol. All right, whiskey is a lot more concentrated. You can see it's 40% alcohol by volume. And so to calculate the amount that you need in order to obtain 5 milliliters of alcohol is going to be less, right? So we got 40% this time. We, again, are looking for 5 milliliters of the ethanol. And that's supposed to be an N in there. And then this time we want to know the volume of the whiskey times 100. So we're going to rearrange the same way, where that volume equals 5 milliliters all over 40% times 100 equals, so 5 divided by 40 times 100 equals, and you can see it's a lot less in order to get 5 milliliters of the alcohol. Great. So, not that you should be drinking any of this stuff, but that's how much ethanol is in a given volume, and you can use a percentage to figure it out. All right, take care. See you soon.